My name is Henrik. I'm a professor at the University of Bergen, and we're participating in this mega roller project. And so it's me and my colleague Volker Röber who have been running this Busenesque model. And so basically our job is to look at the interaction of the energy converter with a wave resource. And so actually the wave resource is a very interesting thing. So if you think about energy, so what actually makes the waves? So what happens is that what you have is that the sun or the sunbeams, they create winds in the atmosphere. So the trade winds, easterlies, and others. And so there you have energy accumulating over weeks to make those winds. And so then in turn, those winds impact the ocean. And so the winds drive actually wave generation. And so there you have energy accumulating over several hours. And once you actually have a wave, you see that there's energy that has been accumulating for a long time. So the energy density of the waves is quite high. And so therefore, it's a very promising energy resource. And so I was very happy to be part of this mega roller project, where I feel we can really improve future technologies. So, like I said, our work package was focused on the wave resource, and so the BOSS model that we've been using essentially gives you a wave a phase resolving forecast. So typically what you have with regard to wave forecasts in the oceans, you have phase averaged forecasts that give you a forecast basically on a grid of, let's say, 1 kilometer size, and you get a forecast maybe every half hour. So every half hour on a grid that has 1 kilometers between the grid points, you get readings of the significant wave height, the wave period, and the peak direction. However, in order to maximize the energy uptake of the mega roller and other wave energy converters, it would be beneficial to have more detailed knowledge of the features of the waves. So in particular, what you see here are so you see long crests, you see short crests, you see circulation patterns, and so you see bottom features, and all of those can be resolved with this nearshore model. So the BOSS, that name stands for Busenesque Ocean and Surf Zone Model. So that has been developed by Volker Röber actually for a number of years, and so we have together then used this model in connection with the Mega Roller project. So let's see. So the basic idea behind this model actually is quite old. So it's called Busenesque model because Busenesque, a French scientist, was the first to write down the equations, and that was in 1872. So it's almost 150 years ago. But the numerical study of those equations is not that old. That was started really in the 70s and 80s. It has now matured to a point where it can be used in operational wave forecasts. So the essential idea of Busenesque was to reduce the problem from a 3D problem to a 2D problem. So you integrate along the vertical coordinate, and so thereby reduce the complexity of the computations. So with those Busenesque type models, you can resolve a lot of features of the wave field. You can resolve wave interference, bottom features, focusing, diffraction, refraction, wave breaking, and also in particular, one thing which is very important is a long period oscillation of the mean water level. So those are called infragravity waves. They have usually a period of about 5 minutes. And so those can be nicely resolved with this model. And I should also say that there are other Busenesque models of similar type. So this is just one actually of several Busenesque models. But anyway, that's the one we have been using. Let's see. Yes. So typical range of applicability, you have to assume that the waves are somewhat long compared to the depth. That is generally true in the surf zone. So you have depth of maybe, let's say, 5 to 10, 15 meters, and the wavelength is generally on the order of possibly 20 meters. So the long wavelength assumption is often satisfied. Braking generally is not uh, modeled by overturning, since we have integrated out the vertical coordinate. So instead, wave braking is modeled as a bore, as you can see here. And so this bore enables us to take out the right amount of energy as the waves break, and the energy is dissipated in the shoaling and braking process. So here are the equations, and they're somewhat complicated. So you have the continuity and momentum equations. Those are straight from physics. I'm not going to bore you too much with those equations, but then so if you actually look at the actual equations that are solved, those are those. So this model is written in conservative variables, so that you don't look at the velocity u and v. So those are the horizontal velocities, but rather you look at the variables h times u, h times v, where h is the water depth. And so this conservative formulation makes the model numerically more stable than some of the other models that are in the market. Um, so here's just one example of a hydraulic jump, which is supposed to model a braking wave, and somehow you see that the red and the blue curves give similar results, which means that the wave, so the energy dissipation is modeled somewhat appropriately. And here again, you see on the left a TVD Riemann scheme that is used in the case of wave braking. And on the right, you see an upwind finite difference scheme that's used in the case of non-braking waves. And so you see on the left, you have some dissipation, which is what we call grid dissipation, which essentially simulates the the energy dissipation due to the wave breaking. Okay, so the BOSS model gives you a numerical solution. It's based on a structured Cartesian grid. It's a combination of finite difference upwind scheme and a Riemann solver for the hydrostatic part, which is simply the hyperbolic part of the equation. You have a stable shock solution for wave breaking. Time integration is done with a Runge-Kutta scheme, and then only wet cells are actually computed. So you often have many dry cells because of run up and run down, but here we only compute the wet cells, not the dry cells. And that leads to a reduction in computation time. So some benchmarks were done. For instance, one of the classical benchmarks is the Mosse-Kirby test from 1992, where a wave flume experiment was done. There they had a wave spectrum with a significant wave height of 7 centimeters. I mean, so again, this isn't a wave flume, right? So very small wave height here. The period was about 1 minute. No, sorry, 1.5 minutes, and the you see the skewness and asymmetry can be computed with those formulas given here. And so basically what we did was to compare the skewness and asymmetry between the measured data from the experiment and the outputs from the BOSS model. And so you see it gives very good agreement. Okay. Yeah, there. Okay. Yeah, another benchmark is the Burkhoff test. And again, here you see that the experimental data are given by red circles and the numerical results by black curves, and very good agreement is reached here. Okay, so so we've done now in the framework of this project, we have looked at several geographical areas where the mega roller or possibly other wave energy devices could be deployed. And so what we looked at was basically to simulate the wave field over some time. And so we look, so here you see on the left essentially a map. and on the right you see significant wave height indicated in red. We see where the energy is concentrated, and so this is important both for maximizing energy uptake and also for the safety of the equipment, of course. So right, you possibly don't want to have the mega roller deployed in a region of frequent wave breaking, because that will put unnecessary strain on the equipment. Okay, so there's some more pictures here of different locales where the mega roller could be deployed. So you see here areas of very high significant wave height. We've also made a study of the Peniche site. So this is actually a location where the mega roller is already deployed, and so the white dot here in the two panels actually indicates the location of the, well, it's actually not the mega roller, it's the location of the wave roller, which has already been deployed. And so you see here some interesting features. You see the wave field on the left, you see significant wave height on the right, and you see, due to the bathymetric features, so basically the bottom topography, you see regions of focusing where it's dark red, and then regions of lower significant wave height where it's more going to the yellow. So with those types of assessment, of course the AWE team, or the people in charge of the deployment, can choose the right location or the best location where they think they can get the best compromise between energy uptake and stress on the equipment. So all this can be done with the mega roller, and it's summarized in our report, the deliverable. And so we've done some recent publications. They're summarized here. And that actually concludes the talk. So thank you very much.